Well, welcome back. This is going to be part 1 of chapter 2. So I wanted to chunk chapter 2 into 2 parts. The first part being kind of a chemistry review, and the second part being a more biology review. I'm going to try to get this to be 20 minutes again, so let me get my timer on. You should give yourself about half an hour to an hour of time here, so that you can stop and pause the video and check your textbook and maybe make some notes and things like that, just like I encourage you to do in the first chapter. So let's go ahead and jump into the second chapter here. This first part is going to be about the chemistry of it all. So atoms, compounds, and molecules, and hopefully you remember that from your chemistry class. We remember that atoms are the basic unit of chemistry, and it's what makes up matter, anything that takes up space and has mass. Mass is the quantity, the amount of stuff in matter, and that's different than weight, which is about the gravitational pull, but on Earth it's equivalent. And so since we're on Earth, we're just going to use mass and weight interchangeably. If you remember from chapter 1, and I had mentioned there was a pyramid of levels of organization, and at the bottom are your smaller particles like atoms and molecules, and then as you go up, you get to cells and tissues and organs. So we're at the very tip, at the very bottom of that pyramid with our atoms. If you remember your protons, neutrons, and electrons, protons being positive, neutrons being negative, neutrons being neutral, and electrons being negative. And the protons being the atomic number, the protons and neutrons being the atomic weight or the atomic mass, and the electrons having to do with charging and forming ions. So within an atom, you have a nucleus, not to be confused with the nucleus of a cell. The nucleus contains your neutrons and protons. And then the electron cloud is where you're likely to find electrons, although you may have drawn the Bohr model with the concentric circles. It's a good way to kind of visualize the flat atom, but remember it is a cloud. Atoms interact, so electrons are what makes them interact, makes them either stick together or the electrons are passed over, lost and gained. I left these in again for chapter 2. Let me know if they are getting in your way or if you are using the review, because this is over 150 slides. So, a lot of it is, it's a slide that you may just kind of skip over. So let me know. Throw me an email, but pause here and look through the review and the learning outcome and make sure that you've got it. Okay, atomic number, total protons, mass number, total number of protons and neutrons, an element, only one kind of atom. Hydrogen is going to be very important. You probably talked about hydrogen in your biology class, but hydrogen is the simplest. It's a part of organic compounds, but it also forms water, and there's a big section in here on chapter 2 about water and it's important, how it's important to living things. Isotopes have different number of neutrons, and so it's heavier or lighter than what's on the periodic table as your, like your basic hydrogen, for example. Hopefully you remember isotopes. We do use isotopes in anatomy. Well, in medicine, I should say. Isotopes are used as tracers, so they can help find things like cancers, but they can also be used to find other issues with like the digestive system. Atomic mass. So I don't know if you learned about this in chemistry. You might have about the carbon-12 being kind of the standard for the formation of these atomic mass units. Atomic weight, it's very close to the mass number. There is a difference, but we don't really focus on that in anatomy. This is very detailed, and I'm not sure why. But hopefully this is a reminder of your chemistry. Trace elements. So trace elements become important when we start talking about some of the system. There is a really nice, page 53 has a table that this might pop up here. You may not be able to see it. That has some information about the 4 most abundant elements, the carbon, hydrogen, oxygen, and nitrogen, and then the trace elements as well. And this is the table on page 53. You can take a look at what some of them, what their significance are, and kind of see what systems from last chapter they would be involved in. Another review, another time to pause, look over the artwork, review these questions, and then come on back. Atoms are generally neutral. We won't get, well, we'll talk a little bit about electrolytes, but we won't get to the digestive stuff in this semester. But we do talk about the electrolytes, which have to do with the electrons and charged atoms. But basically electrons, they occupy the energy levels, and they can be, that Bohr model of those concentric electron circles or shells, kind of like a planetary model, which is actually, there's a bunch of pictures of those on page 54 and 55. The outermost level is the valence shell. You probably remember that. Those are the ones that do the most reacting, either sharing or lost or gained. Atoms with unfilled outer shells are reactive. When I used to teach chemistry, I used to say, think of a hotel, think of, 4 rooms being the orbitals, and you fill the room one at a time, and any empty spaces, there's a tendency for that atom to react in some way. If their outer shell is completely full, all the hotel rooms are full, they are, the atom is more stable, or it's also known as inert. And that would be that all the way to the right, that whole column of noble gases. Electrons, elements with unfilled valence shells are reactive. This is kind of the same thing as the last slide. Atoms that have gained or lost electrons are no longer neutral and become ions. There are some important ions to talk about in anatomy, and we kind of, when we get to especially the muscles and the nerve, we talk about those again. So here is an example of a cation that has lost an electron and become positive. Here is an example of an anion which has gained an electron and become negative. Pause here to make sure that you remember all of your chemistry. Most common chemical bonds create either compounds or molecules. Compounds are made up of 2 or more different elements. Molecules can be the same element, and usually are the ones you talk about with covalent bonds. Ionic bonds, remember the ones that are transferred. So one atom has gained, one atom has lost. So you have a cation and anion that are held together by an electrical charge or electrical attraction. For example, salt. Sodium chloride was a common example of that compound. Covalents, no, this is the example of salt. Covalent bonds, those are the ones where they're shared. If you have 1 pair of electrons shared, that's a single covalent bond. If you have 2 pairs of electrons shared, that is a double covalent bond. These are the ones that make up living things, mostly the organic compounds, which we'll be talking about in the second part here. Non-polar molecules are the ones where the electrons are equally shared, and so there's no slight charge on any end of it. Polar molecules are where they are unequally shared. Water is a very common polar molecule. The electrons are unequally shared towards the oxygen atom, and so you can see here it has kind of this slight negative charge, whereas the hydrogen atom, since the nucleus is exposed, there's a slight positive. Okay, go ahead and pause here and review this section. 3 states of matter: solid, liquid, gas. Solid, these are just kind of the characteristics of the molecules where the particles are held together tightly. Liquid, where it has a constant volume, but it takes the shape of its container and they're less tightly held together. Gas, the particles are not fixed, so there's no volume. You can compress or expand gases. That was one of my favorite units in chemistry, is when we started to look at the gases and how they fill spaces. Water is the only one that can exist in all 3 states of matter, only a natural one anyway. And here you know solid water is ice, liquid water, and then water vapor in gas. Hydrogen bonds are what hold those water molecules together in all 3 states of matter. And these are very important. For example, DNA is held together by hydrogen bonds, so it's a very important attraction in anatomy. Water constantly forms and breaks into a liquid state. I mean, you can jump into a pool and disrupt the hydrogen bonds in water. When they're frozen, they're locked in place. And that accounts for the expansion. And then when you break all the bonds and you heat it, becomes a big, ooh, my goodness, I'm so sorry. Where are we? Yikes. Okay. And compared to other chemicals, water has a very slow rate of evaporation. You might have seen an insect kind of walking on the water. You may have had a drink and you've been able to pour it to the tippy top and it has that kind of curve over the top. That is the surface tension is responsible for that. And that's the idea that the hydrogen bonds are sticking together, acting as a barrier. Water is a very important solvent. If we talk about, for example, the fluids of the body, when we talk about tissues of the body, the ones that are more fluid like blood, water is the solvent for everything that is dissolved in blood and everything that is held in blood. Here would be a good time to stop, but also take a look at page 60. There's a section 1 review that you might want to take a pause and see if you remember how to do all that stuff from chemistry. The next section is about chemical reactions. I'm just going to keep going because this is all the chemistry, and I've kind of divided the chapter into the chemistry portion and into the biology portion, and I'm hoping that this doesn't run too much over 20 minutes, but we'll see. All right, so chemical reactions. That's how cells function, through chemical reactions, especially when we start talking about the systems. When we get to the point of talking about systems, they're all controlled by chemical reactions. If you remember, the reactants are what goes into the whole reaction and products come out. Metabolism is the definition of metabolism is any of the reactions in the body at any moment. Each cell is a chemical factory, then cells work together as tissues, and you can call that a chemical factory as well. Your cells provide energy, they're able to maintain themselves and repair themselves, they're able to grow and divide. Certain cells can secrete, certain cells can contract, so there is just an enormous amount of metabolism going on in a cell. Work, I don't know if any of you are in physics or you took physics, but work is the movement of an object or change in the physical structure. And when we talk about work in cells or outside of cells, we can talk about the system, like the muscular system, being involved in work, or you can look at the microscopic, the cell level, and look at, for example, the synthesis of molecules. Kinetic and potential energy. Kinetic is the energy of motion. Potential is what's stored, and there's a lot of potential energy stored with these chemical reactions within a cell. The cell has to find the best way to use that energy for kinetic energy. So potential energy involves a lot of reactions like, if you remember, cellular respiration, okay? We store the energy in the food that we eat, and then that energy is broken down into smaller pieces, which we can use for kinetic movement. Okay, go ahead and pause and review the idea of work and the chemical reactions. Notations. This is when you were making the little subscripts and superscripts and coefficients and all that jazz. You need to make sure that even in anatomy that if you're talking about CO2, that 2 is little. It's a little subscript. So it's a chemical shorthand, but it also is universal, so it needs to be written precisely. For example, H2O, 2 atoms of hydrogen and 1 of oxygen. You know, H2O2 is hydrogen peroxide, so that's 2 atoms of hydrogen and 2 atoms of oxygen. And here's some subscripts, and I mean, this was talking really about coefficients, and this is talking about subscripts about a molecule, but it indicates how many molecules. We don't get into moles in anatomy. Arrow indicates the yields, so that's the direction of going from reactants to products. Balanced equations. We are not going to balance the equations, but if we were to reference a particular chemical reaction, you should understand that it is a balanced equation. Ions are indicated with pluses or minuses. Since we do talk about ions, especially in muscles and the nervous system, make sure that those are superscripts and it's appropriately labeled as a cation or anion. This visual is on page 62. This is kind of a neat representation of how it's notated versus how it actually, not actually, but how you would visualize it with the atoms and molecules. Take a second and pause and look over page 62. That's a really good graphic. A mole is mentioned here because that is a given amount in chemistry, although we don't really do much with it except mention it right here. And this just gives you a visual of what 1 mole of oxygen and 1 mole of hydrogen would look like. Again, it's just a unit, just like a dozen eggs. The molecular weight of something can be calculated using a periodic table, and you know, 2 times 16 is 32. 2 times 1 is 2. More about chemical notations. We are going to be using the nearest whole number. We're not getting into any decimals when we talk about molecular weights. And we're really not going to be calculating any of this. So just kind of review through this, make sure you understand it, and take a pause and review this section. Okay, the basic types of chemical reactions. I'm at about 20 minutes now, so we're going to finish up this section and then move on to, oh good, I'm really close to the end of this, so it'll be about 20, 25 minutes. Okay, the types of chemical reactions. Physiology is based on these reactions, so if you don't remember them, take a minute and make sure that you're reviewing. So decomposition indicates a breakdown. So this AB yields A plus B is a good visualization of a decomposition reaction. So these are when molecules are being broken down. An example is the digestion of food. Hydrolysis is when you break it up. This is happening, or I'm sorry, when you build it up. This is happening in the cells all the time, okay? No, I'm sorry, what am I talking about? Hydrolysis, it is a specific type of decomposition where you use water to break it down. So this water is used to break down this molecule, and when you break down an H and an OH, it's an H2O, one of the H's becomes part of one of the products, and then the OH is attached to the other product. So it's a way that water physically breaks down a molecule. And this happens with a lot of your organic chemicals. And I don't know if you remember that from biology, but hydrolysis was one of those that was specifically talked about. Catabolism is another type of decomposition reaction. Basically, this is a broad term that we talk about breaking down covalent bonds and releasing kinetic energy. So again, it's an umbrella term, so it can actually almost be interchanged with decomposition as long as it's not a hydrolysis. Okay, now we're on to synthesis, which is the opposite of a decomposition. This is the building up, sorry about that. And it's about building larger molecules from smaller pieces. Dehydration synthesis, or it's also called a condensation, is when water is formed. So it's the opposite of hydrolysis. When you take a dehydration synthesis, you have two molecules here with an H and OH involved. And so the A and the B become one, and then that H and OH combine to become water. So dehydration means the loss of water. You formed water, it's being lost from this product. Anabolism is the opposite of catabolism. It's another umbrella term. It's used for synthesis reactions. Equilibrium. It's important to understand that a lot of the reactions, a lot of metabolism within a cell is at equilibrium, meaning the forward reaction is happening just as often as the reverse reaction. So that's how we kind of maintain homeostasis, maintain this chemical balance. In exchange reactions, so these are the ones that you probably call it single replacement or single displacement, or double replacement, double displacement, where you swap. So this A swaps with this C, so A and D become together. These can be synthesis or decomposition reactions. Okay, that is maybe the end of this section. Was I going to talk about enzymes? We'll talk about enzymes right now. Okay, so enzymes are involved in chemical reactions. They lower the activation energy. So it lowers the amount of energy that's required to make the reaction actually go. Enzymes are really important when we talk about anatomy, especially when we talk about any type of physiology of the systems. So enzymes, even though you have a chemical reaction, you may not mention the enzymes. Any metabolism in the cell has an enzyme that is catalyzing the reaction. They function as catalysts. So in chemistry, you probably call them catalysts, and in biology, you call them enzymes. But they are proteins that have this function to lower the activation energy. And that's a visual that you may have seen before. Metabolic pathways. So again, something that was simplified probably in biology and maybe chemistry is that an enzyme is involved in one single chemical reaction. As you can see, there are several enzymes, and it is a pathway. It's usually a very complex pathway that doesn't go one way, but sort of like goes in all different directions, because these different products like B, C, and D can be used in different parts of the cell for different reactions or different physiological pathways. Exergonic and endergonic, this just describes the reaction. Does it overall release energy to the outside? Then it would be exergonic. Or does it overall require energy? And that's endergonic. Metabolites are substances that are synthesized or decomposed in our bodies, but they are done so with the help of enzymes. Nutrients, some of these enzymes work best or work at all with certain nutrients. We get a lot of these from our diet, from organic compounds that are broken down. Inorganic compounds can help us as well, especially the salts. Okay, macromolecules, this is where we kind of fuse into the biology of it. And the macromolecules are the large molecules made up of smaller monomers. So if you look at here at the dehydration synthesis, these monomers are built up. So this would have an H, this would have an OH, water comes off, you'd form a polymer. The reverse, so this would be broken, by the addition of a water, which would put an H on one and OH on the other. Okay, we're gonna, sorry it was a little bit longer, but here's where we're going to break, and then I'm gonna start talking about more biology, biochemistry type stuff in the second part.